Hello, everybody, and welcome to our SMB session. My name is Rafał Szczesniak, and together with my colleague Jeremy Hitt, we are going to share with you some of the results of the work that we've been doing over the last few months on migrating SMB2 clients connections from cluster nodes to other cluster nodes. We are ready. I am sorry about the missing visual background behind me. It did not quite work, so I've chosen most plain and white wall in my flat. And but we are dressed up nicely, and we do wear trousers. So let's start. This is about high availability. And in today's world, everything needs to be constantly available. Any interruptions are not welcome. Especially the enterprise grade storage needs to be available all the time. Whenever you need to do anything that ends with a reboot, your customers are going to tell you not this year, or at least not this month. But still, even highly available storage needs maintenance from time to time. Hardware breaks, we need to upgrade software, we need to fix bugs. Sometimes we have security fixes. At that point, customers don't really negotiate. So there is never really a good time to reboot the system, including our laptops. How many of you have postponed the reboot, the upgrade, ending with the reboot on your laptop for as long as you could because it interrupts your work? Well, I'm in that club quite recently, actually. So with scale-up clusters, the problem is a little bit less painful because we have multiple nodes that we can choose some of them to keep up and running and let others be upgraded and or fixed and otherwise be inactive. But that still means we have connections to those nodes that we would like to migrate away so that no one is interrupted. We can safely operate and do any maintenance necessary. If we do it right, then hopefully there is a chance that no one is going to notice anything, and we can upgrade individual systems without even breaking out anyone's window. So within existing methods that we have in the most recent versions of the protocol, which is SMB3. SMB3 as a dialect allows us to use something called witness service, which was released along with the very first version of SMB3 dialect. It's a part of continuously available share scenario, and it's tightly coupled with it. Witness is a separate service running on a separate protocol, but the idea is that we have clients connecting to continuously available shares, opening persistently files on those shares so that they can recover the state in case of any disruption, connection loss, or a server crash. And Witness provides information should something happen to the connection or the server or even the operating system on the node, and lets the client know immediately that something's going on, and the interface, the IP address that the client has connected to is unavailable, so that clients can immediately react, reconnect, and assuming the persistent handle open, they can recover the access to the file and continue without any interruption. It's not very common, primarily because it's mostly Windows implementation of Witness that's available out there. But that's one of the ways. Another is share redirection, which is a reconnect error response. That's an SMB 3.1.1 feature, allowing to move clients closer to where the data actually lives in store. Although this one can be disruptive depending on how applications handle the error code. That's according to Microsoft spec. Both methods work at the share level. They are not node level, which is something we would like here. But we could still pretend that all of our shares are continuously available. And if we have CA shares, then we may be able to move connections away. But still, that's SMB3. And well, first of all, many SMB3 implementations do not support CA or witness. They do not have those implementations. There are still SMB2 clients out there. And SMB3, because it's just a dialect, stripped off those CA features, it acts essentially as an SMB2 client. And with SMB1, well, it has retired, rightfully so, so we don't really care. With SMB2 clients, there is no good way of handling this kind of problems because the protocol does not provide any mechanism. But what we'd like is making the transition as non-disruptive as possible. We obviously and certainly do not want to lose any data because that's the opposite of non-disruptive. And we would like users not ask a local administrator what just happened because I've been disconnected. So it all starts with the DNS. We connect to services and clusters here with the DNS name. The methods that we are describing here and discussing are not going to work if you connect to an individual node's IP address, because then we do not have any way of telling the client what are the other IP addresses within the cluster. So we would have to use the CA level methods, and that again is SMB3 domain, assuming you implement that. So that's not an option. We have to rely on the DNS resolution, and that's what we're going to use with something called Smart Connect, which is a service that runs in one of its clusters. One of the nodes can run Smart Connect service, which is a smart DNS server. From the client point of view, it's just another DNS server, resolving the cluster name to an IP address. We reserve one IP address for that service, so that's going to be the price that we have to pay. And then we have one of the nodes assuming the responsibility of resolving this kind of request. Smart Connect can respond with a different IP address of different node every single time when requested. That's for load balancing. It may do it in round robin fashion. It may do it according to a different policy. It may take several factors into consideration. But also we can let Smart Connect know that we start maintenance on a node. The node is going to go offline. So Smart Connect should not give out those IP addresses after it's been requested. And that's how Smart Connect is going to stop responding with those IP addresses to new connections. So we have one problem solved. New clients are not going to reach us when we are doing something with the node that's going to be disruptive. In a way, the node and its IP addresses are going off the grid. Here's how, simply put, it works. We have a client coming. Every single client has configured a DNS server, probably more than one. So it's going to request a resolution of domain name of a cluster that it's trying to connect. The DNS server is going to tell him that the actual DNS server handling this particular cluster is here. So the client is going to repeat the same question, this time to Smart Connect node. Well, the node running Smart Connect. And in response, Smart Connect is going to return the address of another node. It's not going to be the same. Like I said, Smart Connect requires one IP address for its own purposes, and it's not going to participate in any network conversations. So when another client comes, we have another redirection, just like the client before. And with that, Smart Connect is going to respond with another IP address for the purpose of load balancing. So let's pretend we have yet another client coming. It's already been redirected to Smart Connect. Smart Connect would respond with the node. Normally, for the purpose of load balancing, it would be, once again, the node that's been previously used. But if we have a node that we are trying to take offline, we do not want to give those IP addresses. So the node needs to tell Smart Connect that it's going offline. So Smart Connect can not use those IP addresses in the pool of active ones and just point client to node 3, which is up and running and perfectly fine. So that's the idea behind the resolving the DNS. And since we have new incoming connections handled right now, new clients are not going to bother us. Now we have to do something about the existing connections. Jeremy?
Thanks, Rafal. So we have oplocks and leases, and we certainly don't want to lose any data. And to that end, we need to address the oplocks and leases. SMB has mechanisms called oplocks and leases that allow clients to cache file data. Oplocks were SMB's first attempt, first iteration. Leases, essentially the same, a refinement of oplocks and work in a similar manner. And what they essentially act as a way for the client to tell the server that it will be doing cached or local operations on the file, and the server should let the client know if another user needs access that would be affected by that caching. So when we're initially disabling, we want to disable this caching. So we know that we're going to be disconnecting the client, so we want to disable that caching. So when we start the process of draining connections, we first prevent clients from taking out any new oplocks or leases. We then will give the client the opportunity to flush its cache before we disconnect them. Obviously, any data loss is most definitely not a non-disruptive experience. So reviewing how a normal lease operation works. The client wants to open the file with a lease, knowing it's going to do some local caching. So it sends a create with the lease to the server. The server opens the file on the file store and notes the lease with the file store so that if there's any conflicts, they'll be notified. The response goes back to the client, and at that point, the client can do operations on the file completely locally, no network traffic back and forth about this. But if some other user, either the file store or another client, if there's some kind of conflicting access needed, the file store will then alert the server that it needs to break that lease, which then sends a lease break notification to the client. The client then is given the opportunity to commit any cached work, write files back out, get them response back, and at that point it's completed updating the cached work so it can acknowledge the lease break to the server, at which point server tells the file store client's all done so it can grant the conflicting access. Now what we want to do is, a similar situation, we want to utilize the same mechanisms on the client, but we want to, instead of wait for conflicting access, induce a lease break. So, as we saw in the previous slide, oplocks or leases are broken or downgraded, when somebody else is accessing the file. Now we want to, we're migrating the client from this node. We want to force this. So very similarly, same setup, the client opens the file with the lease, goes to the file store, registers the lease, does that, and then the client can work with the cached file. Now, when we need to drain this node, we have a forced break that we need to do. And by that, we send a similar lease break notification to the client. Client has the same opportunity to commit the cached work to and from the server. As data is written out, then it acknowledges the lease break. The difference here is now we get the lease break. Now we actually tell the file store to remove that lease, and then the operation is done. Client should no longer be caching data, and it should be safe to disconnect. Back to you, Rafal.
Okay, thank you. So we need to disconnect, but the fact that something that we're hoping and counting on is that clients can reconnect. And they really do. Virtually all the clients that we have tested have the ability to reconnect when the connection drops, which means that if you drop the connection at a opportune moment, then the client's going to rebuild the connection. Maybe this is because of the SMB legacy as an older protocol from the older days, where when the networks were not so reliable and as available as they are today. But most importantly, if the moment is good and the connection drops, the client reconnects and rebuilds the state, the end user doesn't really even notice. It's business as usual. Files are still open, directories are still listed, things are fine. So ideally, when we disconnect in order to have a client reconnect, we could try to have a client connect the next time to another node. That would be the idea. And the question is, to what extent is this possible? What is the right moment in the first place? You don't want to do that too early. From the tests that we've been running, SMB to connection has to be established. You do not want to disconnect before at least the user has authenticated. So disconnecting when the SMB connection is negotiated is not an option. I mean, it may work, but it has high degree of probability that it's going to be disruptive. With connection authenticated is much better. With share connected is just as good as authenticated. And the tests we've been running with Windows, Linux, and Mac OS clearly show that the negotiate request is not a good moment. This shows you the result of disconnection of Windows clients after receiving negotiate requests, delaying for a moment and then dropping the connection. And the delay that we've tested was around 1 second, 5 seconds, and 10 seconds. As you can see, the only roughly successful client here is Windows 10. Windows 8 and 8.1 were a little bit slower, but they still could do something. However, there are generally too many occasional connection errors. Interestingly, it doesn't work if you choose the delay too short. The longer you wait and then drop the connection, the better the result. But still, the success rate clearly is not very high. And it's completely hopeless with Linux and Mac OS clients that we've tested. They just cannot connect. One disconnection at the negotiate phase and it's gone, errors out, and that's it. Interestingly, even though there is no success at all, Mac OS keeps sending keep alive requests on SMB level when we reach the 10 seconds of delay before disconnecting. With session setup requests and then again delaying for 1, 5, or 10 seconds and then dropping the connection, situation looks much better. There are no errors. Windows 7, 8, 8.1, and 10 nicely reconnect and recover the connection. This time, Windows 8.1 reacted the fastest, although the difference between 10 and 8.1 wasn't really so large. Linux and macOS, again, have the same problem. They just cannot reconnect. With 3 connect requests, similar results. Windows is reconnecting in every single case, and Linux cannot reconnect. It just gives up, and user does have this this disruptive experience. macOS is an interesting case here because it's going to keep trying forever. It never stops. Even if you have this dialog box with the connection attempt and you cancel it because okay, you've given up, you don't want to, you're not trying anymore. macOS underneath is going to keep trying. So if you keep your favorite packet sniffer like Wireshark, for instance, open, then you're going to see that it's going to keep reconnecting until you reboot the node. It's very persistent, although with no chance of success here. So the idea here is that we do not want to drop the connection too early. We want to allow clients to establish the basics, possibly even open a few directory handles, because that's where it starts. Even if a few files have been open, but nothing else happened, the clients can still handle their case and reconnect. So we sort of just play with time and trying to slow down and disconnect. It helps if we delay the responses a little bit, because that keeps the clients under control, slows them down, but they still think they are doing something. And this buys us more time to clean up other connections, because there may be many. We do not want to wait for too long. Larger transfers, meaning like megabytes of files written, are really hard to break and get away with that. If you are in the middle of a large read and there are many read requests being responded, then with so many reads outstanding, if you just break the connection, then client's going to consider that things really went south, and it's going to signal an error, and we are disruptive. If possible, it's good to find a moment where there's as few reads and writes pending as possible. Ideally, if it's none, and it's possible, because these days, clients, especially Linux and macOS, they tend to open a file, do something, and close it. In many cases, those are the operations. So especially if it's a small file. So that's finding a fortunate moment to have a client with no outstanding reads or writes is possible, or at least as few of them as possible. We have to accept the risk that the fortunate moment may never come, and we may have to just drop the connection, and yes, the client will notice that. So with reconnecting, what we are hoping, if you remember one of the previous slides, we are hoping that the disconnection is going to make the client resolve the DNS name of the cluster again. This time, get another IP address and connect somewhere else. With that, Windows is pretty good. With every single reconnection attempt, it's going to DNS-resolve the name again, get another IP address, and just go away. So that's a very desirable case. There may be clients that cache the DNS resolution. So even though the client, the client-side implementation is going to request the DNS resolution, the system-level caching service is going to give the same IP. So they may require more patience. They may require several rounds of disconnections. That may help actually, because if within those several rounds of disconnections, things are from the beginning, basically, then there may be few file opens, few read or write transfers, and that may give us more hope and chance to not disrupt the connections heavily. However, there are clients that are just not going to go away. They are very persistent, and so long as the TCP connection is available and they can connect to port 445, then they just keep trying, and they will never resolve again and try something. So in that case, the only thing we can do, because that's the last chance, we've shaken off everyone else. We stop accepting at port 445, which basically means closing a listening socket, and we drop the stubborn guys. And the moment we do that, some versions, notably older version of Linux client, and I believe that was Ubuntu 16 that we tested, do get the message, because they are resolving the DNS name again, and then obviously reconnecting somewhere else, which is a outcome that we rely on. But the newer version of Linux CIFS driver, they do not. Possibly that's an improvement from some other point of view. Might be something to consider as an option for mount CIFS to allow that kind of behavior, because it would improve the client migration thing. macOS never does that. macOS keeps trying, and then if you just stop accepting connections, it's going to tell you that things are wrong. But there is light of hope, because the end user is given a choice to ignore the interruption or just disconnect everything. If it ignores it, then that location mounted is still there. And the moment the user tries to access a file or directory within that share, macOS is going to resolve the DNS name again and go away. Granted, it's not completely non-disruptive, but that's still something. So what are we asking for? Because it's quite simple, actually. If you're implementing SMB clients and your connection keeps dropping, then that means the server may be trying to get rid of you. Do not just keep trying to the same IP address, just try to resolve the DNS name and try again. It doesn't have to be the very next attempt, like with Windows. For performance reasons, you may try several times before you give up and DNS resolve, but just please do it. It may help. It's not a big change. It should help and improve scale out scenarios when you have to migrate clients away, and you don't have too many means at your disposal to do it non-disruptively. It may probably help with clustered storage, the cloud storage scenarios too. If you're looking for hints that someone's trying to do that, then your connection is slowing down. That means the response times for your requests are longer. They take longer time to arrive. If you have originally been granted oplocks of leases, you no longer have them. You've been either broken in terms of leases or oplocks, or you even don't have them anymore because you've requested but you haven't been granted it. So there is no client caching anymore. It's quite clear. It's also possible that you are connected not to one of us, but another server being passive aggressive and playing nasty tricks with you. For that, we do not take any responsibility. We're just trying to politely move you away somewhere else. Now, the wish list. Like originally mentioned, Witness is a service running at a shell. Well, I mean, running. It's applying its policy to shell level. It's allowing you to be told that there's something wrong at the shell level. Wouldn't it be nice if we had Witness at a node level or system level, meaning that something's going on with the SMB server itself, so it's not going to be available, please go somewhere else. Not the shell, the node, the system. That will be a very nice extension. And then the status code that we could return from either session setup or tree connect. If there were not like with the reconnect, which can be handled by the application level. Just for the client, notice that your next request may be never served, or your connection may be dropped suddenly because we are about to shut down. This kind of status code would be very nice to provide the redirection at the SMB level. So with that in mind, thank you very much. We do answer any questions that you might have by the appropriate channels that the SDC provides this year, which I believe is Slack channel. So we are happy to answer any of your questions on Slack. And with that, thank you so much, and see you on the next SDC.